So the title of this tutorial is Writing Your Own Thorn, which is, well, it's a little bit of a lie because we're not actually going to write a thorn, but we might actually just modify it a bit. Okay. This is not really intended for you to run these commands live right now, although if you're quick, you probably can. But essentially, there is I showed before a link, and the link will get you to a Bitbucket repository, which does have some information about actually downloading the Thorn I'm going to be talking about now. And this contains some information, also contains some configuration files that one could use to get this Thorn up and running. Okay. Now, before we actually get to the Thorn itself, let's just talk a little bit more about how you write a Thorn with practice. Okay, so let's first consider something kind of basic. We're going to have a Thorn, and we're going to think about the Thorn as containing, we're going to imagine our Thorn contains a scalar variable, f, for lack of a better name, and it will also contain the gradient of that scalar variable. And so here's how, and then in a file called interface.ccl, we tell practice about these variables. And you can see here that we have my scalar, which, so we have our function f, which is called its scalar, and it belongs to a group. The group is called my scalar. And what we can see is that this is a grid function. It's going to be potentially going to be an evolve field, so it's going to have multiple time levels. And we're going to tell practice that in fact is a scalar variable. And we're going to do something similar for the gradient of f, except that here we're going to define 3 different fields corresponding to the x, y, and z derivatives. And we're going to tell practice that the tensor type is not scalar, but is u for a vector. And then within another file, which is the schedule file, we're going to have to declare that we're going to have storage for these variables. Otherwise, they will, no storage will be allocated. But once we get to the point of having grid functions, we have to have some understanding of how the memory is laid out. So as far as your code is concerned, a grid function is basically a pointer to a one-dimensional array. And that one-dimensional array is then mapped to a logically three-dimensional, in general, three-dimensional object. This is kind of a translation between the array index and the logical index. So the point right at the address corresponding to the pointer that are given is going to be corresponding to the point 0, 0, 0. The next double over is going to be the point I equals 1, j equals 0. And that will continue until you get to the end, until you run out of all the i's. Then there's some possible padding. And then finally, you're going to get the first non-zero j index. That repeats until you get to the first non-zero k index. The padding is determined at compile time. And so you don't want to write a code which depends on it. So there are macros which we can use to translate between the logical ijk and the actual offset in our one-dimensional array. And this is the cctkgf index 3D macro. Okay, and then here's an example of some looping which we're going to do to calculate our derivatives. So let's see. We can loop over I, j, and k. If we're going to do writing an explicit loops like this, always go in the reverse order. So I goes first, or I is the innermost loop, and k is the outermost loop. And here we're just showing a simple way of constructing a derivative. This point IP1jk corresponds to the point I plus 1. I m1 corresponds to the point I minus 1. I'm going to skip, it's something similar for j and for k, but basically you can calculate a second order active derivative hopefully somewhat it makes sense. We're basically taking the point I plus 1, the point I minus 1, taking the difference and dividing by 2 dx. And in this notebook, I've just added some other common cactus objects that if you're writing your own Thorn, you probably need to know about. I'm not going to go through each one, but basically, these objects are either macros themselves, or they're arrays. But basically, these are things that your code has to be interacting with. So, for example, as we're going to see, cactus functions always take CCD arguments. I say always, depends what kind of function we mean. And then there is this. There are these other ones, and we'll talk about them as needed. Okay, and then I'm not going to go in the details here, but as you go through this Thorn and reviewing it, there's additional information here in this notebook, which will tell you about how things are actually, how the Thorn is actually set up. Okay. The actual code that we're going to evolve is this. It is Maxwell's equations extended a little bit to give a constraint damping. Not that it's necessary in this case. It's Maxwell's equations in the presence of permittivity, a non-zero permittivity or permeability. Okay. This other notebook, the Maxwell Systems and Algorithms, also actually generates, although that's not necessary here, it actually generates the code, or generates the interior of the main loops. This is not how you should be writing your own Thorns. There'll be tutorials later on how to actually get modern tools to build the code for you, but this basically kind of gets the job done. And I was just playing with it, see if I can get Python to write my C code for me. Okay. So if you follow the instructions in order to get this tutorial Thorn, you're going to, and by the way, what I mean is in the Bitbucket page. So if you actually were to run this in the appropriate directory, you would get this, and let me go into repos tutorial. In repos tutorial, you're actually going to see a few directories. The config files contain some things which is useful, at least mostly for building on a CentOS 8 machine. There is the notebook directory, which contains copies of the notebooks I was just showing. But the most important one is the simple Maxwell directory, which contains the actual simple Maxwell Thorn. Okay, and within that directory, there are 4 important files, and I'm kind of go through them in turn. So the first I want to look at is interface file, and our interface file's got to basically, it says that simple Maxwell, well, implement simple Maxwell. We could have called it any name we want, but it's probably a good idea to call it the same name as the Thorn. And it inherits from grid. So inherits means that your code can actually one of the things it means is that your code can access variables from other Thorns, well, Thorns that they inherit from. So grid is perhaps we're going to need to actually look at the XYZ coordinates. And so we're going to need to inherit from grid in order to see those coordinates. And also, what the heck, I use loop control to do the looping. We'll see that a little bit later. And here's the variables we need. So we have our system involves the electric displacement, the magnetic field, and the magnetic field. And so we're defining the components of the D field and of the B field. And we also have to define variables that hold the time derivatives of those fields. And so we have another two. Will look very similar, but you notice that these ones, am I not? Okay, these ones only have one time level. That's because we don't evolve the time derivatives. We just need them. Okay, those are some scalars. I'm gonna skip those, and then we have some constraint fields, and we'll talk about those a little bit later. Constraint fields, those are actually going to be, in this case, those are actually they're going to contain the value of del dot D and del dot B, which should be 0. And then I have below that what I call standard boilerplate code. And it's safe just to copy this code and put it in your file. It's harmless. In this case, what it does is it allows my code to directly access the method of lines Thorn to register variables with them. And I think there's some boundary conditions that allows us to work with. But just cutting and pasting that in place is fine. The configuration file is oftentimes empty. In this case, it just has that it requires loop control. So we're going to ignore that one. Oftentimes the most complicated file is the schedule file, which is where we determine what routines, trying to tell Cactus what routines to run and when. Okay, so first things is we do need to provide storage for our variables, and that's done here. The single integer inside the brackets just corresponds to how many time levels should it get storage. And the evolved variables are going to get 3, and the non-evolved variables don't get, will effectively get 1, except, well, since 1 is the default, we don't have to specify anything. Okay. So then continuing on, I'm going to skip for the moment this function. We'll come to that later. Oh, there's a raised hand. So can you ask your question?
Yes, sir. Just a quick question. Could you just eliminate what does it mean that there are 3 time steps that the variable is saved in these 3 time steps?
So yes, okay. So basically, and it's gonna what it corresponds to is you need to do an operation which requires information about what the field values were in the past. And one thing where you classically need that information is if you have subcycling in time and you're doing prolongation, you may need to basically interpolate between time levels. So for example, the course level could be ahead of the fine level, and then you would use an interpolate, but you want to essentially fill in values on the fine level from the course level. So you'd interpolate between, let's say, the current course level and past values on the course level in order to fill in particular missing points on the fine level. This is also, but that's not the only case that could be needed. You might also want to, say, interpolate the value of a field at an arbitrary XYZ coordinate, and that point may lie, let's say, in a course, may happen to lie in a course grid, but you want the value corresponding to the current time on a fine grid, and again, you would have a time interpolation. So if you're going to be interpolating those values, the variables, or prolongating them, which is kind of the same thing, then you need to provide more time levels. So, did that answer the question?
Yes, it did. Thank you.
Okay. Let me just see if I can. Okay. So I want to get back to really nitty-gritty stuff later on. So for right now, I want to look at just kind of the basic structure of our Thorn. We have to somehow initialize our variables. And so we're going to initialize them in a time bin called cctk initial. We're going to be doing method of lines calculations So somewhere along the way, we have to schedule our routines which calculate the time derivatives in that bin. So that's what this simple Maxwell right-hand side is. Now, simple Maxwell right-hand side actually is not a function; it's a group. But we'll schedule functions in that group. And simple Maxwell initialize is a function. You can kind of see the difference. One is that it's not called a group, and the other is, you see this one says its language is C. Okay, and then here's the actual algorithm. So this was actually a trimmed down Thorn that originally did more stuff, making it more complicated than it needed to be. So this simple Maxwell right-hand side interior, that's an actual function which does that. It calculates the right-hand side of the Maxwell equation in the interior. I mean, that's not ghost zones and not boundary. There was originally other things here, right-hand side near the boundary and so on and so forth. But I've cut those out. And so that group of originally that group of functions were all scheduled inside this simple Maxwell right-hand side group. Now there's only one function in that group. Okay. We'll get back to this schedule file, but now I want to go into the source directory and look and see how those routines are actually implemented. So if I go to initial, first, some more boilerplate stuff. We always got to include cctk.h and arguments and parameters. And this loop control.h is going to be necessary because I'm going to be using loop control to actually do the looping. Okay. And so my function, simple Maxwell initialize, that's the one which was mentioned in the schedule file. And you see it takes as arguments, cctk arguments, which is a macro which will expand to, well, something internal to however Cactus decides. We don't need to worry about what it expands to. Probably just cctk.gh, but or not. And if I want to use any of the variables, I have to add the macro declare cctk arguments. And if I want to use any parameters, which I haven't really talked about before, but those parameters are things that you can set in the part file, which will change the way your simulation works. If I want to use any parameters, I have to include declare cctk parameters. And I just made this function, have it look at various parameters and then call other functions. So I want to look at this simple Maxwell pulse. Okay. Okay. And I'm going to ignore most of what I'm ignoring are just things which were just to basically to read some parameters and make some changes based on values of parameters. But the core loop here is the important one. Okay. So I'm defining a loop using a loop control macro. The syntax is, well, we're using variables ijk. We're going to start from I equals 0 and go up to I is equal to ni, number of points in the I direction. J goes from 0 to nj. K goes from 0 to nk. Oh, and then finally, we also have to specify how big the arrays actually are. They happen to be, in this case, ni by nj by nk. Okay. Here's where I'm going to use the cctk gf index. This will get me the index corresponding to the point ijk. And here, as you can see, I'm just getting the x, y, and z values. Z has been rescaled, again, just for convenience. Okay. Let's skip that detail. And so now we can see we're in actual variable where the variables are actually getting set. So the psi b and the psi d, those extra variables, those are set to 0. And then dx and by are set to generate what's effectively a plane wave moving in the z direction. And then the loop ends, and that's it. Okay. Okay, so let's look now at the interior algorithm. So the interior algorithm, it's going to have a slightly different looping structure because since we're taking derivatives, we're going to need ghost information. And so we can't loop over all points. Okay. So here, my main Maxwell loop, again, it's using variables I, J, K, but it starts at the point I is equal to what I'm calling ghost X. So skipping a certain number of ghost zones, and it's going to skip a certain number of ghost zones at the end as well. And the same thing happens for J and for K. And these are those I plus one, I minus one variables, indices that we talked about before. Okay. And then I'm just going to write down my derivatives. So the x derivative of bx is going to be given by that formula, and y derivative, z derivative, etc. And so those are the derivatives. We're just going to kind of skip through them. All the derivatives we need, there's a bunch. And then finally, I might want to make this a little smaller. We have our actual evolution equation. So the time derivative of bx is given by apparently the x derivative of psi b plus a bunch of other terms. And we've provided the time derivative of all the variables, all the evolved variables, and then the loop ends. Okay. And so if you were to take the code that I've just shown, skipping all the things I just skipped, what would happen is you'd have the code, it would compile, and you'd run it, and it would do nothing. Because, unfortunately, what we have to also do is we have to tell Cactus, hey, these are variables that we need to evolve. Okay, so we have to tell Cactus about them, and that is actually happening. That doesn't happen in a CCL file. That actually happens at runtime. So here's where we actually do that. We call, for example, mole register evolve. This is saying that telling the method of lines Thorn, which is just a separate Thorn, that we want to evolve a variable, let's say dx, full name here, and its time derivative was going to be stored in a function called .bx. I figure that's as good a name as any, and we do that for all the evolved fields. Okay. But there's another kind of field that we also are interested in. These what is called constrained fields. Constrained fields, that's something which constraints fall under, but basically it's any field where essentially you can where the update of that field is to obtain directly from the new values of the other field. So for example, the CD is just the divergence of the D field. So you update the D field. Once the D field is updated, you can directly compute the divergence of D and the divergence of D. So that update is not done through time derivatives. It's done once dx, dy, dz are already evaluated. You then can immediately differentiate them, and then you get this CD and CB. Okay. And in fact, we can look at the constraints calculations themselves. And so the constraint calculation is going to look basically like the interior calculation because it's just derivatives. But now we just have a divergence of the D field and the B field. And notice that what I'm setting here is not something like a CD dot, it's CD itself. Okay, why we have to tell mole that it's a constraint variable? It's because it has to know. Mostly it's because I want it to be updated in the right time in the right bin, which we'll get to in just a second. Okay, so let's go back to some of the things I skipped. So we have to register our variables with the method of Thorn, and that's done in a particular bin. In this case, the bin is called mole register. So And then also you might notice that this option says global. Basically, when you're interacting with directly with the mole interface, you're going to be working in global mode. When you're directly working with grid functions, you're working in local mode. In local mode. Local mode is the default. If you don't put anything there, it'll just be in local mode. Boundary conditions, also, there's going to be a bunch of boilerplate stuff. Basically, you have to, even as in our case, we're only going to be using periodic boundary conditions. But even so, we have to register, we have to tell Cactus, hey, we got grid functions, they need a boundary conditions applied to them. And so again, my recommendation when dealing with this is start with a Thorn, which actually contains this, which contains applications of it contains the schedule, and copy and paste, to fit your Thorn. Okay. So at this point, one last thing we haven't talked about is parameters. Okay, so there's going to be some things that you want your code to, choices you want to be made at runtime, not at compile time. So for example, what the initial data might be, some parameters corresponding to the evolution system, some parameters which describe, we're going to have a wave crossing a material, some parameters which describe the wave, parameters which describe the material. Those are all things which are handled by, basically we define parameters and then we can set their values in the parameter file itself. So we're going to now take a look at that. In fact, actually, I'm going to go back to this notebook. So here I've kind of tried to document, or at least organize, a parameter file. Okay. And so let's look at, for example, that we want to set up the grid. Yeah, this we'll do a run without AMR, so the max number of refinement levels is 1. We're really not going to do any prolongation, so I didn't really need these. But what the heck, out of habit, I set the prolongation order. And here's where I'm setting up the grid itself. So I'm basically saying X goes from -5 to 5, similar for Y, Z goes from -5 to 15, and how many cells there are per direction, how many boundary points there are per direction, and the number of boundary points is going to be equal to the number of ghost zones here, because I'm using periodic boundary conditions. Then the boundaries are going to be periodic, and we're going to use RK4 as our update method. Just for fun, we're going to add dissipation, although for this system it's not necessary. And here's where I set my initial data. And set the properties, and finally some debugging and some output. So at this point, we can test out the code by trying to run it, which will take long enough that we won't actually do that. We'll just look at the result. And so the particular profile that I ran is very similar, except in the interest of time, I use much fewer cells. Okay. So we have a run. What do we do now? So I've run the code, but I do have some output, which we can make use of. we could look at things like, what output is here was determined by the par file. For example, I could look at the norm, whichever one this is, the L infinity norm of dx versus time. And that might not be all that interesting. If that was a constraint violation, that would be interesting. But what we can also do is use various tools to actually look at the results. So I'm going to use visit. By the way, if anybody, well, it's doing it by itself. If you have any questions, just directly interrupt me. I'm not going to be able to see the chat to tell. Okay. Okay. So this is showing dx. This is on the xz plane. And no, this is dx on the xz plane. This is either a visit or whatever. It says it's the xy plane, but it is the xz plane. Okay. And let's go see what happens, just kind of using the default. Our wave hits the medium and it kind of gets affected by it. And we have periodic boundary conditions, so something just keeps happening and will keep happening for a while. And also I'm not keeping well, let me actually let me fix this scale. Okay, so we have a wave which moved through and interacted with something. What it interacted with? Well, you can check that as well. There we go. That's the medium. It's 1 over epsilon. So we basically have a large epsilon in the center in this spherically symmetric distribution. And that was what the wave was interacting with. Okay. So at this point, I would actually like let's actually do some actual editing. So one of the things that you might want to be looking at is what you might want to do is some analysis calculations. Now, the right way to do this, all the output is there. The right way to do this is, if you're really doing analysis, is just have a script which calculates some analysis quantities. But let's not do that way. Let's actually go through the exercise of modifying the Thorn to do our calculation. Okay. And so one of the missing things that we have is, for example, we don't calculate the pointing vector. Okay, maybe we want to calculate the pointing vector. So let's see what we would need to do. The first thing is the pointing vector is not going to be evolved. It's just E cross B. So it's basically going to act just like we had it for our constraint variables. Okay. In other words, once you know E and B, you can get the pointing. pointing values. Okay, but we are going to need to. So since it's like a constraint variable, let's kind of steal some what we got from. Let's steal this section from our constraint variables, but we'll give it a different name. I don't know, call it a ball flux. Not ball pointing. Okay. Of course, the pointing vector is going to be a vector, so not going to be a scalar. And I don't know, we'll call it Sx, Sy. Yep. Oh, if only I knew. Presumably U is upper index. Yeah, I figured it's probably upper index vector.
What else could it be?
Just a vector, because that's the common notation for a vector.
I think there's also UU, which is a
UU, which is yeah, so yeah, except that as far as this is concerned, upper and lower indices count the same.
So, yeah.
Do you actually need D?
In Jonathan's multi-patch system, you worried about it, yes.
Oh, okay.
Where this is coming from, apparently, that was before my time. And I think you also might worry about it if it was a fluid quantity. It had a metric determinant in there.
Yeah.
But
Yeah. So well, okay. So we're, by the way, so where this tensor aliases are going to show up for our purposes is just going to be in relatively simple boundary conditions. So in that case, you know, like if you think about it, if you have reflection symmetry, let's say around the z-axis, around the xy plane, then a scalar field at a plus z would have the same value at minus z, and the x component of velocity would be again the same, plus c and minus c, but the z component of velocity would switch sides. And so when you're applying boundary conditions like that, you really want Cactus to know, well, you must have Cactus knowing what the object is and how it behaves under whatever symmetry operations you're actually doing. Okay. So we've told Cactus that we're going to want variables Sx, Xy, and Sz. We have not provided storage for it, so we better do that. Okay. Now that we've provided storage, the next thing is to figure out when should this be called? But let's use the fact that this is acting pretty much like a constraint variable. So let's just use the same bin where the constraint was. Okay, and we can see that constraints are actually run in most pseudo-evolution. Okay, so probably want to schedule our routine there. And you know what, looking at this code, we have let's look again at this constraint. So the constraints, we have something is evaluated. We're going to call a synchronization for the constraints. Then we're going to call some boundary conditions. I'm interested in the boundary conditions. And synchronization, we could either do it or not. Depends on how, it's not a choice because our equations are algebraic. We could in principle evaluate S at every point, or we can decide to evaluate it only in the interior points and use synchronization. But in the spirit of just copying what's already there, let me just, I've already forgotten what I call this. So I'll just declare that I'm going to synchronize the pointing vector with the scalars. And I have to worry about a little bit about those boundary conditions because they seem to be important regarding the scalars. So let's see about that. And here's where it's all going to fall to pieces because there's no way I'm doing the cross product in my head. In fact, I'm going to give the false cross product. Yeah. Okay, so that's not correct, but it's off by. Okay. It's actually not so bad. I think I got that. So I wrote down the formula for D cross B. If I divide by epsilon, I should get E cross B. And then I probably want to do a cyclic permutation, but you know what? There we go. I'm documenting it's a known error. Rather than directly trying to code that out. Now, if I were to compile, hopefully compiles, and run it, it still wouldn't be correct. But probably a good idea to see if it at least compiles. And it's not going to be correct for two reasons. This case, it won't be particularly critical. We never did actually register the variable to be constrained variables. We never registered that. And the other thing we didn't register is boundary conditions. And so if we were to actually do this, run this, and we would find that there'd be issues on the boundaries. Okay, so let's fix that. Okay, so symmetry boundary, let's look for, I think it's CE, the one I want. So we can see that in order to register for our boundary condition, we're going to need access to the group name, which is going to copy that over. And okay, we've now registered. We've told the boundary Thorn that hey, these variables are going to need boundary conditions. And we're missing just one more thing. We need to register that these are constrained variables. Okay. And maybe that will compile. Oh, it did. Okay. So now that we got to compile, let's see if we can get it to run. I have my par file. I'm going to copy an executable. And let's see. Saying this should run for 60 minutes. Nope. Run for 1.
This page has been blank.
Oh, my screen went blank. Stop sharing content. Start sharing content. Stand by. I'm starting up. Okay.
Where are you?
Okay. Okay, so just I'm just going to directly run this on my laptop. Okay, not going to bother submitting it to anything. There's nothing for me to submit to. It's running. Most importantly, it has not seg faulted at this time, which is probably the first thing that happens whenever I finish compiling code. Okay, so we let it run, and hey, maybe it'll work. Right. While we're doing that, oh, well, I knew that wasn't going to work. You probably cannot see any of those words, but so let me quit because I. Okay. So it's gonna checkpoint and dump and so I can even restart this. But if I go into the directory, well, where are the variables I just defined? I spent all this time working with. Well, they're not output because my part file didn't know anything about them. So let's look at our IO. And I really, really wish I remembered what this was called. I think it was simple Maxwell evolved pointing. And I just want to get rid of this stuff. And maybe it won't crash here either. Who knows? Woo! That's promising. And of course, now I'm going to really regret the fact that I had that deliberate bug, because the only non-trivial component of the pointing vector is the z component. And guess what? And that had a bug because I couldn't be bothered writing the actual cross product. Well, let's see what happens. Yeah, that's what happens. Okay. Oh, something. Yeah, I suppose once the wave hits the material, there's going to be non-trivial x and y components. And all we have is the X component, because I just copied the X component over twice, rather than properly filling in the Y and the Z. Okay. So, any questions? Yes.
Why did you use it in control?
Because
Right.
last year I didn't.
Because what, sorry?
Last year I didn't, and I wanted to make a change.
Okay.
Honestly. If you look at, so in that, the Git repository basically has different branches. You'll see there's tutorial 2023, which is the new one, and then there's tutorial 2022, and then there's one master, and master has the most, the code has the most features. And then 2023 was cut down, 2022 was cut down, and then 2023 I figured I should make some change. Also, I figured it's more in the spirit of what future codes will be looking like.
All right.
I have a few questions if you don't mind.
Sure.
So the first question is, say, if I don't want to put a material, but I want to put maybe a ground metal sphere in the middle and apply the Dirichlet boundary condition to the potential, how would you do that in the boundary?
Oh goodness. I don't even want, right now I don't even want to think about how to do an immersed boundary. But difficult. One has to think about it. Yeah, there are certain things that, yeah. If you wanted to treat, okay. Let's talk about cheating, and let's talk about treating it properly. So if you wanted to do it properly, then again, what you have is a boundary condition inside your domain, and the boundary condition is not compatible with any of your coordinate directions. So that's a tricky one. A cheating method is you don't introduce a conductor. You don't introduce a pure conductor, you introduce a resistor. And then you could modify the equations to include resistance. And an even better answer is, in that case, when you're really talking about a real problem, you would use a code which was actually designed to solve the problem. This is just not designed to handle real electromagnetism.
I see. And the second question is, so I think Jay earlier in the morning also mentioned about like vertex base or face based variables. So in this case, do you have to define them differently? Do you have to calculate them differently?
Yeah, so this is Cactus, where everything by default, or the only thing it actually supports without trickery, is vertex centered. I'm looking at Roland, not as a blame, but as to correct me when I'm wrong. I suppose that if you don't give any flexibility, you don't give any options, there's no difference between vertex centered and cell centered.
Not in universe.
Yeah. Well,
I see,
the
cool.
AMR is vertex centered, right? So.
AMR can be self-centered.
Okay.
Interfaces allowing.
Okay.
And we just don't usually use it because then it puts the metrics, which are samples at the center of the cell, and then your restriction becomes then inaccurate.
Okay. But as I just coded everything up by default, without specifying anything, then I can interpret this as entirely vertex centered.
Okay, I see. Thanks.
Any other questions?
I have a technical question.
Sure.
I don't see a link to the repository you mentioned in the beginning. Could you show it again?
Okay, sure. Okay, let me see where I have that. Oh, there should be a notebook called, it might be called Cactus and Design Intro, which will actually have the link. It's right there. But let me actually show you the correct link, this link as well. second, let me get rid of.
Yes, there is indeed link in the tutorial.
Yeah. So there's a link in the tutorial notebook, but in case you wanted to copy that down, just do a search for well, that will get you there, I think. Any other questions? Okay. Okay, in that case, I'll just quickly check the chat. Okay, in that case, I think I am done here. Well, if you wanted to play with this Thorn, in principle, you can on the tutorial server. But so maybe Roland or Steve, if somebody wanted to run this, how would they actually basically all what they would need to do is essentially run that command there? What would they need to do? Or is not
Well,
really
I mean,
possible?
you could open a notebook and you could just put that command in a cell and with
Yeah.
percent bash and execute it. Like you could, I mean, that might work. I'd have to try it.
Yeah. Okay.
Yeah, in interface.cca.
Yeah.
There's like time equal to GA
Yes.
and time levels equal to T.
Yes.
So could you please explain that?
You want me to explain that?
Yeah.
Okay, so well, basically, so the standard variable that we're evolving with, those three-dimensional variables, three-dimensional arrays, those are called grid functions, and that's what type equal GF is. So it's a grid function. There is also scalars, which is a single value known to every process. There are arrays, which are just more general objects, which could be distributed in different ways. But in general, you're working with grid functions. Now, time levels would be how many time levels does Cactus keep track of? Well, how many time levels in that file? It's how many time levels in principle can Cactus keep track of? And then in the schedule file, there's also the storage. And so let's say you say, I want 10 time levels, but only provide storage for 2. It's only going to keep track of 2 levels, although it could keep track of in principle 10. Okay, I think I'm finished then. You have a question, or you just want to end it? Well, then, thank you very much.